Hello guys, welcome to the class of software engineering. In this session, we will discuss component level design. Let's start with component definition. Object Modeling Group Unified Modeling Language Specification defines a component as a modular, deployable, and replaceable part of a system that encapsulates implementation and exposes a set of interfaces. A component communicates and collaborates with other components and entities outside the boundaries of the system. There are three different views of a component. First is an object-oriented view, in which a component is viewed as a set of one or more collaborating classes. Second is a conventional view, in which a component is viewed as a functional element, that is, a module, of a program that incorporates the processing logic, the internal data structures, an interface that enables the component to be invoked and data to be passed to it. Third is a process-related view. Here, emphasis is placed on building systems from existing components maintained in a library rather than creating each component from scratch. Let's first understand the basic difference between cohesion and coupling. In the diagram, modules are shown connected to each other, and, also, inside the module, there are functions which communicate with each other. So here, we can say modules are shown connected to each other as coupled components having intermodular strength among the modules. Whereas inside the module, the functions which communicate with each other. Case cohesion. Therefore, cohesion is the intramodular strength. Now, cohesion can be defined as the single-mindedness of a component. That is, module should perform single-minded function. It implies that a component or class encapsulates only attributes and operations that are closely related to one another and to the class or component itself, which should be maximized. And coupling can be defined as the degree to which one program unit, for example a class, module, subsystem, relies on other units. It is a measure of the strength of the interconnections between elements, which should be minimized. Cohesion, being the intramodular strength, can be ranked from high, the most desired one, to the worst, the least desired one. While designing a system, cohesion should be maximized. Now, let us start with the desired form of cohesion. That is, functional cohesion. In functional cohesion, a module performs one and only one computation and then returns a result. Then comes sequential cohesion in the hierarchy. In sequential cohesion, components or operations are grouped in a manner that allows the first to provide input to the next and so on in order to implement a sequence of operations. Then comes communicational cohesion. Here, all operations that access the same data are defined within one class. Then follows procedural cohesion. In procedural cohesion, components or operations are grouped in a manner that allows one to be invoked immediately after the preceding one was invoked, even when no data passed between them. Then comes another interesting form of cohesion, that is, temporal cohesion. In temporal cohesion, operations are grouped to perform a specific behavior or establish a certain state, such as program startup or when an error is detected. Now, is the turn of logical cohesion. Here, elements of component are related logically and not functionally. Several logically related elements are in the same component and one of the elements is selected by the caller. Last is the coincidental cohesion. Here, the parts of the component performs multiple, completely unrelated. Coupling is the intermodular strength among connected modules. It is a qualitative measure of the degree to which operations and classes are connected to one another. The objective is to keep coupling as low as possible. The kinds of coupling can be ranked in order from highest, worst, to lowest, best. Let's start with highest form of coupling, content coupling, which is least desirable. In content coupling, one component secretly modifies data that is stored internally in another component. Common coupling. Here, a number of components make use of a global variable, which can lead to uncontrolled error propagation and unforeseen side effects. Then comes control coupling. In control coupling, operation A invokes operation B, and passes a control flag to B, that directs logical flow within B. Consequently, a change in B can require a change to be made to the meaning of the control flag passed by A, otherwise an error may result. Next is stamp coupling, in which a whole data structure or class instantiation is passed as a parameter to an operation. Then comes data coupling, which is the most desirable form of coupling, in which operation A passes one or more atomic data operands to operation B. This means, the less the number of operands, the lower the level of coupling. In the diagram, you can see that the most desirable form of coupling, data coupling, is loose coupling, which is characterized by less interdependency, less coordination and less information flow. This signifies that loose coupled components are easy to maintain, reuse, and test. Whereas, on the other side, worst type of coupling, that is, content coupling, is tight coupling, which is characterized by maximum interdependency, coordination, and information flow among modules. The textbook Pressman, R. Software Engineering, a Practitioner's Approach. McGraw-Hill is referenced while organizing these slides. Hope you all enjoyed the session. Happy learning and thanks for joining us.